Hey there, and welcome to this explainer. Today, we're going on a bit of a journey into the mathematically rigorous but absolutely fascinating world of petroleum engineering and well deliverability. We are going to trace the exact life cycle of a drop of oil, from deep underground all the way up to the surface, and we're going to decode the precise physics that actually dictate how it moves.
But first, we need to shatter a super common myth. When most people picture an underground oil reservoir, they kind of just imagine this massive, subterranean lake of liquid, right? Just sitting there waiting to be slurped up by a giant straw. Well, that couldn't be further from the truth. Reservoirs are actually made of solid rock. It's microscopically porous rock that acts like a giant, highly pressurized sponge, and the oil is trapped inside those tiny pores. So the real central question of well deliverability isn't simply how do we pump the fluid? It's how in the world do you coax fluid out of solid rock thousands of feet below the Earth's surface?
To answer that, here's the roadmap for our mini masterclass today. 1. Squeezing oil from rock. 2. The 3 states of flow. 3. Clogs and superhighways. 4. Irregular shapes and boundaries. 5. Predicting the well's future. And finally, 6. When water joins in.
All right, let's jump right into Section 1, Squeezing Oil from Rock, the foundation of fluid dynamics. Literally everything in well deliverability starts with an expression from way back in 1856 known as Darcy's Law. In its radial form, this equation tells us exactly what controls the flow rate of oil into our well. You can think of this equation mathematically kind of like a car. Permeability, which is just the rock's ability to transmit fluid, and the pressure gradient, well, they act as the engine pushing the oil forward. If you have high permeability, you've got a massive engine, but the fluid's viscosity, its thickness or resistance to flow, acts as the brakes. If you're dealing with highly viscous oil, those brakes are clamped down hard. It's this constant, ongoing battle between the pressure pushing the oil and the fluid's own internal resistance that determines how much actually makes it to the wellbore.
Moving to Section 2. The 3 states of flow. A well's timeline.
You see, a well doesn't just behave the exact same way forever. When it first starts producing, it enters what we call the transient flow phase. We also call this the infinite acting phase, because for those first few hours or days, the well doesn't even know how big the reservoir is. It hasn't felt any physical boundaries yet, so the pressure just drops rapidly right near the wellbore. But eventually, things change. If the well gets pressure support, say from a natural underground aquifer pushing water in to replace the oil, it hits steady state. Here, the pressure at the reservoir boundary stays constant, and everything reaches this nice stable equilibrium. Finally, we reach pseudo-steady state. This happens after months or even years when the well finally feels the physical limits of the reservoir. Maybe it hits a fault line or a closed boundary. At this point, the pressure everywhere in the entire reservoir starts dropping at a constant rate together. Honestly, a lot like air slowly leaking out of a tire.
Section 3. Clogs and superhighways. The reality check. Back in 1949, engineers Van Everdingen and Hurst introduced this brilliant concept called the skin effect. See, when you drill a well, the actual physical violence of drilling often damages the rock right around the pipe, clogging up those microscopic pores with mud and debris. The skin effect is basically a mathematical value that quantifies this damage. Conceptually, imagine it as either a severely clogged drain adding a massive extra pressure drop to your system, or, if the engineers do their job right, it becomes a newly paved superhighway for our oil.
Let's actually contrast these two realities. If a well has a positive skin effect, say an S value of positive 10, it is heavily damaged. The math shows the reservoir treats this well as if its radius has shrunk down to a fraction of a millimeter. It's literally trying to drink a thick milkshake through a microscopic cocktail straw. Conversely, engineers actively try to achieve a negative skin effect through a process called matrix stimulation, like pumping acid down the well. By dissolving those rock blockages, they might achieve a skin effect of -2, which effectively multiplies the well's radius by 7.4 times. And this brings up an absolutely mind-blowing number that illustrates the math behind hydraulic fracturing. When engineers artificially induce fractures in the rock, they can achieve a skin effect of -6. Now, when you plug a -6 into the well deliverability equations, it multiplies the effective wellbore radius by an astounding 402 times. You haven't actually made the physical steel pipe in the ground any bigger, but mathematically, as far as the reservoir is concerned, the drain just got 402 times wider. That is how you unlock massive production from otherwise stubborn, tight rock.
Which leads us right into Section 4, Irregular Shapes and Boundaries, the engineer's puzzle.
In textbooks, wells are always perfectly centered in these beautiful circular drainage areas. In reality, they're constrained by chaotic, messy geology. So, to account for this, engineers use Dite shape factors. Notice how a well perfectly centered in a circle has a shape factor of 31.6. Centered in a square, it's 30.9, almost the same. But what if geology forces your well into the upper right corner of that square? The factor completely plummets to 4.5. And this is a huge deal, because the source data shows us that simply being stuck in that corner rather than the center gives you an automatic 10% reduction in your daily production rate, and that's even if the rock and the pressure are exactly the same.
Section 5. Predicting the well's future. The engineer's ultimate tool. Okay, so how do we actually bring all these formulas, boundary shapes, and skin effects together to forecast a well's financial lifespan? Well, that brings us to the inflow performance relationship, or the IPR. The IPR is essentially a three-step balancing act. Step 1, you calculate what the reservoir is physically capable of delivering based on the pressure and the rock properties. Step 2, you determine what the surface pipes, chokes, and wellbore hardware can actually handle. Because, look, the reservoir might want to hand you 1,000 barrels a day, but if your surface pipe is too small, you literally can't move it. And step 3, you find the exact intersection between what the rock wants to give and what the surface can accept. That single intersecting point, that is your actual production rate.
So here is how this builds into predicting the future. Using a specific calculation from our source, example 2.9, engineers create pseudo-steady-state IPR snapshots. Imagine taking a snapshot of the well's capability when the reservoir pressure is a really robust 5651 psi. Production is high, everything is great. But as you produce that oil, the average reservoir pressure naturally depletes. So you take another snapshot down at 4500 psi and then another one at 3500 psi. By mapping these parallel downward shifts, engineers can predictably forecast exactly how much the flow rate is going to drop over the years. It allows them to map out the economic decline of the asset long before it ever actually happens.
And finally, Section 6, when water joins in, late life realities.
Up until now, our equations basically assumed oil was the only fluid in the rock. But that's a luxury of a young well. In the real world, petroleum reservoirs always contain some water, known as connate water. Early on, it just sits there, it doesn't move. But as the well matures, free water starts flowing right alongside the oil. This means oil no longer has a monopoly on those rock pores, it has to share the flow paths. So we actually switch from using absolute permeability to effective permeability, tracking both of these fluids simultaneously using what we call relative permeability curves. Suddenly, your well isn't just producing oil, it's producing a mixture. And that water-oil ratio begins to aggressively climb, very often exceeding a ratio of 10 parts water to just 1 part oil.
And let me tell you, this completely shifts the economics. To ground all this complex math into everyday reality, our source describes the phenomenon of stripper wells. These are mature wells that eke out less than 10 barrels of oil a day, but they pull up massive, overwhelming amounts of water right alongside it. And here's the truly staggering fact. In mature petroleum areas, these low-producing stripper wells often constitute the overwhelming majority of all producing wells. The entire operation fundamentally shifts from managing oil to managing the sheer cost of lifting and disposing of water.
Which leads me to a final thought I want to leave you with today. We've decoded the physics, the regular boundary shapes, the pressure drops, and the life cycles, but knowing that the vast majority of mature wells are out there pumping more than 10 times as much water as oil, and with millions of these mature wells operating globally right this very second, is the future of petroleum engineering actually just an exercise in water management? It's a huge reality shift, and it all comes back to the core rock mechanics we've explored today. Thanks so much for joining me on this explainer, and keep questioning how the world around us really works.